Okay, I hope everyone can be able to hear what I'm talking about. My name is Roger Smith once again. So as usual, we are going to have this lecture, and we start recording. Okay. Okay, members, welcome to this lecture. Today is 16th March, 2024. So we are building from what we looked at in the last lesson, where we looked at the OLS as an estimator. And if you recall very well what we ended with, we looked at the property of ordinary least square being blue. I don't know who remembers how to define that. What is it? Oh, yes. So blue is best linear and biased estimator. So we are saying that we need an estimator of our parameters to be the best linear and biased estimator. So throughout this lesson, we are going to look at our topic to build on that topic of the blue OLS, or best linear and biased estimator, as the OLS, by building on the Gauss-Markov assumption or Gauss-Markov theorem. These Gauss and Markov were statisticians who made some properties or assumptions of the ordinary least squares regression. So throughout this topic, we continue discussing the properties of the ordinary least square estimator, and we extend our discussion about the OLS estimator being blue. So in the next slides, we discuss what are the qualities of this estimator. What does it mean to be blue? Moving forward, we start with the very first assumption, where we say that the estimator should be linear in parameters. Look at this population equation that we give. Y equals beta 1, beta 2, plus beta 3 up to beta k, xk plus the mu. If you recall very well what we talked about, beta 1, sorry, here this is supposed to be beta 1, beta 2 up to beta k, are the parameters or the constants of interest that we're estimating. So it means that when we are given this model, we are looking for the values of these betas. And we also know that mu, which is sometimes known as the error term, or the epsilon, the unobserved random term, or the disturbance term, which mainly looks at the variables that we have not included in the model. And what are we estimating? We're estimating y, which y is our dependent variable. So we're saying that y should be linear, a linear function of x. Now, what does it mean? It means that when we look at y being linear, it means that whenever we have an increase in x by a unit, say from 1 to 2, y may be increasing from, for example, from 5 to 15. And if we increase from 2 to 3, maybe we also increase by another 10 from 15 to 25. If we increase from 4 to 5, we may need to increase from 25 to 35. So you can imagine that y is increasing by a given amount, which is similar throughout. So in that case, it means that if we plot the curve for y given x, that is y as a function of x, then we should be able to see a slope or a rise, which is exactly the same throughout all the units. Remember, if y is not linear, then it can take other forms like quadratic. I already mentioned this in the last lecture. Quadratic or being polynomial, it means that the curve is no longer straight, but it is bending, either in the middle, bending upwards. That is what we used to call it the convex to the origin, or bending downwards, that is the concave to the origin. So for our OLS estimator, as the first assumption to be linear, it means we do not have any bend in this curve. In other words, we have exactly a straight line. So that's what we can say about that. Now, what does it mean? If maybe I can be able to show what we are talking about, it means, let me see if I can maybe illustrate this. I don't know if it's very difficult because I do not have my board. I do not have my board here to illustrate that maybe, but let me just don't give that one. I'll see how to do it, maybe to give you further explanation on that. Please bear with me. So the dependent variable y should be linear in function, which is represented by the linear parameters, meaning that every time we measure the beta 1, from beta 1 to beta 2, the parameters are linear in the function. Now the next Gauss-Markov assumption is the zero conditional mean. I had already looked at this. When we look at the sample mean, we said that it should be representative enough to be equal to or close to the population mean. Now, what does it mean? It means that if we draw a normal distribution curve, the middle of it, which we call the mean, from our 100 banana farmers that we have, from whom we have collected data, this curve or this mean we get should be almost the same, like for all the banana farmers in the whole study area. Maybe the banana farmers in the study area are 1,000, but because of limited funds and time, we choose only 100. And if we collect, for example, their age, and we calculate the age, the mean age of these 100 farmers, maybe it is 5. So it means that 5 should be the same 5 that we get, even if we had collected information about the age of all the banana farmers, the 10,000 that we had. So it means that the expectation, the word expectation here in equation, this E means mean. The expectation of the error term or the mu given x1, x2, up to xk. These ones can be maybe farmers. x1, farm 1, farm 2, up to 100, that's maybe k, should be the same, that is being 0, should not be different. So the error term has an expected value of 0 given any value in the x. The x are the independent variables that we are considering. So this gives us the second Gauss-Markov assumption, the conditional mean being 0. We shall wrap up on how to do about all this. Now, the next one we have is the minimum variance. Now, I have already told you, excuse me, that our mean should be the same, should not vary. So it means that even if we calculate the standard deviation, there shouldn't be a lot of variation, a lot of deviation So meaning that also the variance should be very close. That's when we say that if this variance is very close to the population, means there is no variation, there's no difference. Variance means difference. So an estimator which is more efficient is the estimator that is having minimum or no variation or no variance. Therefore, we say it is efficient. Assuming we calculate two OLS value, ordinary least squares value. One is 100, another one is 50. Now, in terms of variance, which one is having the minimum variance? I think you can now already think about that. Yeah, automatically, it is the one with 50. So the one with 50 is having a minimum value. And therefore, it means that it doesn't vary a lot compared to the one with 100. So in that case, it means that our OLS value, which gives us 50, is having a minimum variance, and therefore it is a more efficient estimate. In other words, it is capturing closely to what the population mean is giving. But if you are calculating and then you get a variance which is so wild means so high. I already told you in the class practical, this is looked at in terms of the standard errors. If you calculate and then you have a high standard error, then it means you are making more errors in the measurement than the one with low standard errors. So we can say that the estimator with a very low variance, with a low standard error, is the one which is more efficient than the one which is giving high. Of course, the one which gives a higher value tells you that you are making more errors in the measurement, and therefore the error term is so high. And in that case, it means that it's not giving us the right estimator. So of all the linear and biased estimators, an unbiased estimator with the least variance is known as the efficient estimator. So that one gives us our third property or third assumption of the Gold-Markov assumption. Let us see what other assumptions are. The fourth, this is actually, it's supposed to be the fourth, not the third. The fourth is, I think this is being repeated. So it's the minimum or common variance. Now, of all the linear and biased estimators, the one which is the one with the least estimator is what we choose. Sorry about this slide being repeated. So we are saying that this assumption consists of the variance and covariance. Now, I want to explain these two terms: variance and covariance of the error term, variance and covariance of the mu. So I have already given a highlight of what variance is about. Now, variance being how does the actual or how does the observed value vary from the actual value? How does our sample value vary compared to the actual population value? That's variance. But covariance, which is somehow related. So we are saying that the covariance is assuming we are looking at the variance, the error term of an equation including banana farmers. So we have our equation for banana farmers, and we have our equation for bean farmers. Maybe it is the same farmer who is growing beans, but also growing banana. So we have two models. One is for the beans, and it has an error term, maybe I, mu I, but another model is for the banana farmers, also having an error term, maybe we call it mu J. So we're saying that the two error terms from two different models for bean and banana should not be the same. So when we talk about covariance, it means the error terms which are coming from two different models. So a good estimator should have a constant variance. Sometimes the term used is called homoscedasticity. Homoscedasticity means it has a constant variance. It doesn't keep on changing. You remember the picture that I drew in the last lecture where I was drawing a curve and then I put like a curve going up, a line going up, but with different variations at different points. Now, it means that if it is uniform throughout, that is homoscedasticity. But if there is a variation each time x increases, then now that one takes us to the opposite term, which we call the heteroscedasticity. So the homoscedastic condition of the OLS is written in this equation. So var of the mu term given x1 up to xk. Remember, x1 up to xk, these are the independent variables that you include in the model. Maybe if it's a fertilizer model, you're talking about yield as a function of rainfall, as a function of fertilizer use, as a function of labor use, as a function of, so those labor use, fertilizer use, weather, those are the x's up to xk, depending on what you want to feed in the model. So we're saying that the variance of the mu term given those variables x1 up to xk equals sigma squared. Now, sigma squared means the constant variance for all the values of I. Of course, I can be 1, 2, 3 farmers. I, 1, 2, 3, 4, 5, up to n farmers. Now, that is what variance, constant variance means. Constant variance, it means that var mu given x equals sigma squared. That is constant variance, which we also call homoscedasticity. But covariance means that the model, remember our bean model and our banana model, the mu in the bean model and the mu in the banana model, given the independent variables x1 up xk equals 0. Equals 0 means that the mu I and the mu j are not related. They are independent. That is a covariance of 0. Covariance 0 means that there is no in between or interrelationship between mu I and mu j. I means it's a different model from j. Now, the fourth characteristic or assumption of the Gauss-Markov theorem, or OLS, is what we call the non-autocorrelation. This assumption indicates that the error term should not be independent for all the observations, in the model. And of course, the observations in the model, it means for all the farmers. We go to farmer 1, we go to farmer 2, farmer 3, and you're asking them maybe the same characteristic each time. So we're saying that these characteristics for all the independent variables, for example, age from farmer 1 and age from farmer 2, age from farmer 3 should not be correlated. So if this assumption is violated, then it means there is autocorrelation. And if there is autocorrelation, it means the age of farmer 1 being correlated with age of farmer 2, then it means our results are going to be biased because we assume there's supposed to be some level of independence. But otherwise, if they are not independent, it means they are correlated. And if they are correlated, it means our results, our model, our OLS estimates are going to be biased. So there should be independence of mu, all the error terms, in one model, and also the error terms in another should be different. Likewise, also the age of one farmer should be different from the age of another farmer. Of course, that inverted A, you remember I told you it means for all. So if you don't want to read the word for all I, you just say that inverted A, I, is not equal to J. So it means that there is no correlation, there is independence. The fifth assumption is what we call no perfect collinearity, what we call multicollinearity. I remember explaining this term in the last lesson. We are saying that this is also known as the independence of xj. So it means that our x1, for example, if x1 is the fertilizer, x2 is the herbicide, x3 is maybe another variable. So these x's, and of course you remember y, we have y equals x1 plus x2 plus x3. x1, x2, x3 are different variables. So these variables should not in any way be related. Otherwise, you remember one time I was giving an example that if you are talking about fertilizer, but you're also talking about mulching, and somewhere in the organic fertilizers, there are some mulches. And then the mulches, meaning that they form part of the organic fertilizer. And in this case, it means that if our X1 is organic fertilizer and our X2 is the mulch, then it means the mulch is already part of the organic fertilizer. So in that case, it means there is no independence. There is some collinearity. So if you are given a model before you proceed to analyze, you're supposed to check if there is any collinearity. If there is any collinearity, then it is bad. It means our OLS estimates are going to be biased. They are no longer blue. So we have several tests. One of them, of course, is the variance inflation factor, the VIF test, which we shall see in class during the practical session. You are supposed to first test for all these to find out if there is any collinearity, if there is any linear relationship. Otherwise, if there is some linear relationship, then it is very bad. We do not need to have that. So our sample, and therefore the population, should have no independent variables that are related, meaning they shouldn't be constant. There is no exact linear relationship among the independent variables. That's what I can say. Now, moving forward, as we come to close to the end of this lecture, we look at another assumption, which we call the normality. Normality. And this one, of course, some other econometricians argue that normality is not very, very important. It's not as important as others. But it is also important because we need to combine also other variables to see what this one happens. You remember what I already mentioned, that our mu, the error term, should be normally distributed. This is quite difficult to achieve because if you go to collect data, this is the wish of everyone. But because of some issues with the sampling, some characteristics like age, income, maybe education may not be normally distributed. But if we have already collected our sample through random sampling, we expect that if you go and ask one farmer and he says it's 100 years, if you had not kind of predetermined the next person, you go and then he says I'm 30 years. You go down and says 45 years. Then it means if you're calculating the average, those people are supposed to normalize themselves and give you an average of, say, 50. So all the people will be close to the center, 50. Others will be, of course, slightly above, others will be slightly below. But if you plot the normal distribution curve, they will all come into the center. So we say that that variable, your age, is normally distributed. So for you to be able to get an efficient OLS or a blue OLS, then we need our mu or our error term to be normally distributed for all for all the farmers, for all the observations. I means the observations. So much as people have argued that this is not very, very important, we still think that for the best ordinary squares estimation, give us good estimates of our model. When you're running the econometric model, we need the normality. So actually, we also have a normality test that we do before we continue to do the analysis. So why did we again have to bring the normality? Because we are saying, in short, in conjunction with these other 5 being linear in parameters, being having zero mean condition or minimum variance or common variance, being non-autocorrelated, having no autocorrelation, having no perfect collinearity. So we say, being normally distributed, if you combine with the others, then we can, in short, say that other assumptions, if we are talking about being in conjunction with other assumptions, the error term mu is independently, remember we talked about being independently and normally distributed with mean 0 and variance squared, sigma squared. So this one can be summarized in this short a short structure, short equation, that mu is normally distributed. You look at this side, normally distributed, independently distributed, with zero mean, and sigma square, this means with constant variance. So we say mu is normally and identical. Actually, this one I would prefer that you help me change this n into d. Is independently and normally distributed. Normally distributed, that is ID, not IN. Mu is the slash for normal distribution, then I, that's independent, then D is distribution, and 0 means the zero mean, and then the sigma squared means constant variance. So in short, the Gauss-Markov theorem or assumption tells us that given the assumption of the classical linear regression model, the least squares estimators in a class of unbiased linear estimators have the minimum variance, and therefore they are blue. Best linear unbiased estimator. So if we ask you to state the Gauss-Markov assumption, this is the exact thing that we should be able to look at. Therefore, as I come to the end of this lecture, today we looked at the Gauss-Markov assumptions, or the assumptions of the OLS. The first one we looked at is the being linear in parameter, where our dependent variable y is a linear function of x. So meaning that it gives us the same value each time x changes. We also looked at having a conditional mean. Conditional mean, that means the expectation of our error term given the x1 up to xk is 0, meaning that our mean is very close to the mean of the population. And the third assumption we look at is the minimum variance, where we are saying that we need a constant or a common variance throughout. We need a variance which is so minimum to say that our estimator is close, is giving us the estimates that are close to the population. And that's the term we use, homoscedasticity, and the opposite being heteroscedasticity. So a homoscedastic condition of OLS is written by these two conditions here. We have the val mu given x up to xk equals sigma squared. While the covariance, which we said it is the error term coming from two different models, the bean model and the banana model. And given x should be 0, meaning that there shouldn't be any correlation. That is the independence. And then another one we looked at is the autocorrelation. We are saying that our mu from one model and mu from another should not be correlated in any way. And then perfect collinearity, we are saying that the x's, x1, x2, x3 should not have any relationship at all. They should not be a linear combination. I gave the example of the mulch being a linear combination of the organic fertilizer. And the last one, we are saying that it should be normally distributed. So members, I think that's what I can say about the Gauss-Markov assumption, and that wraps up our fourth topic. So in the next topic, we are going to look at the non-linear models. What I've been dwelling mostly were the linear models. Now in the next lesson, we shall look at the non-linear models, where we shall look at the probit and the logit. The non-linear, it means that x will now have a different effect. We will not have a linear effect on y. And that's why we shall concentrate more on the probit model, the logit model, and the linear probability model. Thanks so much for attending this lecture, much as it is recorded. I was able to do that because today I have to go to visit my daughter at school. So sorry, maybe if you have any further concern, any further questions, we should be able to discuss them in the next lecture. But for tomorrow's lecture on agri-policy, should be able to continue studying physically. I hope that makes sense for you, and I wish you a nice day. Thank you. Goodbye.